Welcome to the solutions video for assignment 3.05, number 1. So we have questions 2, 4, and 5 from section 6.4 of the textbook. And in number 2, we want to use exponential regression to determine the equation of the curve of best fit for each data set. Then state things like domain and range. So our first one, we have the data, which I have already pre-populated into our spreadsheet. So again, we will insert a chart. We will make sure it is a scatter plot. And now this does seem to be an exponential, even though it's a decreasing exponential. So we can expect our exponent to have a negative coefficient. We will add our exponential trend line and label it with the equation. And here we go. There is that negative exponent we were looking for, 9.92 and e to the negative 1.61. So if we wanted to do this as a standard base, e to the negative 1.61 is roughly 1.99887. So without the round off error, this is probably 1 over 5. So if you're doing this on the TI calculator, it's probably going to give you like a 0.2. Now, do we do question 2b or do we not do 2b? That is the question. We'll do 2b. So 2b, we are doing the same thing. Oh, and I neglected to mention the domain and range for the last one, didn't I? The domain for an exponential is all real numbers. The range in that case, even though it's still decreasing, was just y greater than 0. Sorry, we didn't need to sort it. We need to insert a chart. And this one doesn't look as cleanly exponential, but we will do our exponential fit anyway. We will include our trend line. We'll make it exponential. And we'll use the equation. So here the e to the 0.053, which is not that far from 1. So this is going to be e to the 0.053. It's a 1.05 here. So this one is slow growth. But still, anything that we fit on the exponential is going to have a domain of all the reals and a range of y greater than 0. In fact, that is guaranteed. Even if the data deviates from this, the exponential model that the spreadsheets and our calculators use requires that domain and range. So that's a given. It doesn't matter what we're dealing with. So now we move on to question 4. So here we go. Question 4. Samuel and his grandfather record the length and mass of every rainbow trout they caught in the Red Deer River during the summer. He's going to be using it for a science project. We need to build a scatter plot, find the exponential regression function and plot it on the same grid where we plot the points, figure out which mass is going to have a length of 400 millimeters and the length of a fish that has a mass of 1,000 grams. So let us go back to our spreadsheet. So we are going to insert a chart. Now we are going to take our series, insert a trend line, which is exponential, and we're going to label it with the equation. So this alone is enough to answer parts A and B. We have made our scatter plot, and we've plotted the curve on the same grid as the actual numbers themselves. So the next step would be to first interpolate. Right, where are we going to have a length of 400 millimeters? So that's an x of 400. we plug an x of 400 into this equation. So 33.2 times e to the 7.53 to the negative 3 times 400. And that gives us a mass of 675 grams. So that is up in this general vicinity. And then the last one is a mass of 1,000 grams. What is the length going to be? Now that is extrapolating, because that is outside the domain and range of the data set that we have. So for that, we are going to have to actually expand our horizontal so we can keep a minimum of, say, 200. Okay, that was a little bit less. We don't have to go that much less than what we were, but we're going to go to a maximum of 500. And there we can see we're going to end up at a little past the 450 mark. We could also reverse this with a log plot and just enter in the x values. So that's what they're saying. Describe your process. You have a couple of options for the process available to you. We could always graph this in Desmos and say y equals 1,000 and find the point of intersection. Or you could graph this in your calculator and then let y2 equal 1,000, find the point of intersection. So we do have many options there. Finally, question 5. The population of the world has been growing exponentially for about 150 years. We've got the 40-year population in billions. Again, we want to construct a scatter plot, use exponential regression to find a function, estimate the population in the year 2020 to 2 decimal places. And this is one, now that this is in the past, we can actually double check to see if this pattern held, and predict when the population is going to reach 9.5 billion. So let us start with parts A and B. We are going to graph it as a scatter plot. We are going to do an exponential trend line. So here we go. We now have an equation that predicts our exponential growth. So 1.7 times 10 to the negative 12 times e to the 0.0144x. This time I will plot that in Desmos. So that is 1.72 times 10 to the negative 12. But that reads e differently. So we'll actually have to do times 10 to the negative 12 times e. And our exponent here is 0.0144. 0.0144x. I forgot changing tabs takes that out of our function. So we now have the function graphed, although it doesn't really look like it because our y is so low. So we want to be looking at sort of a range. The years go from 1970 to, say, 2050 should capture everything. So let us go back, pick an x from 1950 to even 2050, and then the y-axis should go up to 10. And now we seem to be getting some data here. We're getting somewhere. We've got a graph we can work with. So, estimate the population in the year 2020 to 2 decimal places. Well, when x is 2020, this model predicts a population of 7.38 billion. And we hit the 9.5 billion in the year 2037. That's the not too distant future. Again, I want to, out of curiosity, I'm going to come back here and see how accurate that was, that 7.384. We're going to look at the world population in 2020, and it was 7.7947. So as I'm hearing, not only do we have exponential growth, but the exponent, or the base of our exponent, is actually increasing over time. So even though it's already exponential, that exponential growth is accelerating even beyond those expectations. Anyway, this concludes the homework solutions for assignment 3.05, number 1.